Okay, good morning. In this presentation, I will speak about ensemble data assimilation techniques for geophysical flows and using reproducing kernel Hilbert space and Koopman operator. This is teamwork that we are doing at Inria in Rennes with Etienne Lemin, and there are some PhD students involved, Benjamin Duff and Béranger Hugues for the theoretical framework, and Maljawen doing some geophysical flow numerical simulations. I'm from the fluid mechanics community, so excuse me if I'm doing some shortcuts for the mathematical details. I will try to be as precise as possible.
So maybe put your microphone closer.
Closer, yeah. Just wanted to avoid the feedback. Okay, so we place ourselves in the context of ensemble data assimilation, like it's done in weather forecast or geophysical flow predictions, where we have a dynamical system which is of large dimensions. It can be heavy numerical simulations. Such that it's not possible to run a very long simulation to explore the whole attractor. This is too large. Instead, we stick with what is performed in operational conditions, where we have the possibility to have an ensemble of initial conditions that we are able to generate and run them for a given time. What we want to do is that we have now some observations that arrive, and we want to estimate at best the state of the system. So usually in operational condition, we need to resample and rerun against the system. What we want to do here is basically to don't run against the system and to learn locally nonlinear dynamics. So basically we'll use RKHS roughly to interpolate between ensemble members. And we use a Koopman operator to take into account the fact that we are dealing with a dynamical system and to take into account the linear evolution. And then, so we will build a specific space, or more precisely RKHS family for different times, and we will rewrite an ensemble Kalman filter in this space. So just to fix the idea of the object we are dealing with, so if I speak about physical space, so we are dealing with geophysical flows that are governed by partial differential equations, so this is a physical domain with flow field, velocity, pressure, sea surface height, and so on. And the phase space, that is this kind of pictures, where each point basically corresponds to a given state. So each point is a full flow field. And of course, we have a small number of ensemble members. So if we do inner product in this space, it will be approximated by a sum over this over the ensemble members. So the outline of my talk is the following. So quite classical, but I will speak. I will introduce quickly the classical frameworks of RKHS and Koopman operator, mainly to introduce notations. And then I will present the framework we are constructing, and then some numerical results on the toy problem and on some realistic or semi-realistic simulations. So first, RKHS. So we define a kernel. It's just a function that gives, from two states, gives a scalar value. And this defines what we call feature maps, which are attached to a state of the system. And in fact, they are functions in the phase space where it's the evaluation of the kernel between x and all other possible values. We ask them to be smooth, and it's encoded by an ensemble of P members. We have what we call a reproducing property, where any function in the phase space, in fact, we can evaluate them by doing the inner product. We can evaluate it at x by doing the inner product between f and k at x. It's kind of a collocation in the phase space. In practice, we use them to do, for instance, interpolation or regressions. Here, if you have an ensemble of members, and we have a new members that arrive, we assume that the feature map of the new member can be expanded as a linear combination of the training members, and by inverting the kernel, we can have access to these linear coefficients. So now, thanks to the reproducing property, if we take any observable that belongs to the RKHS, we can evaluate J at X prime just by using exactly the same linear combination coefficient. Okay, this is for RKHS. Now the Koopman operator, so if we have a dynamical system, Koopman operator is an infinite dimensional linear operator that propagates observables in the phase space. So it's, as it has been shown before, we introduce here the dynamical system propagator, phi of x0 at xt. Okay, so it just propagates J a long time. It's a linear operator, it has eigenfunctions, and here if we assume that we have a point spectrum, we can expand any observables on these Koopman eigenfunctions. So the problem of the Koopman operator, it's a difficult object because it's infinite dimensional. We work with in the phase space in a high dimensional space, and can contain a continuous spectrum. So there are plenty of in the literature of techniques to compute them in practice or to use them in practice, like DMD decomposition and all its variants. There are some learning strategies, and there are as well some RKHS techniques to embed this Koopman operator into an RKHS. In all of these techniques, the main point here is to say that most of the time for the learning, we assume that you are able to explore more or less the whole attractor to compute them. And this is something especially for the fixed time RKHS. So what we propose it is the following. This is the main idea of the talk, is that we will consider time-dependent RKHS. And time-dependent in the sense, so we will assume, so we take the feature maps and we say that the feature maps will be transported by the dynamical system. So we assume the system to be invertible and measure preserving. Yes, so here the kernel, we define the kernel, so everything we have to tag the time. Okay, the kernel is time dependent, so the space of the ensemble member, we tag it as well with the time. So we have some feature map, so everything is reproducing property. We have this depends on time as well. In fact, we are able to define the Koopman operator on this RKHS family, because here we have a family of RKHS for different time. And so we write it with a cursive view. It's not exactly the same UTs as the standard Koopman operator, but there is a strong link between them. Sorry. So it's defined like this. So UT of K0, it's KT of X0. So here you see that we are propagating the feature maps, like does the Koopman operator onto observables. Here there is a detail, we attach it to theta of X0, so it's attached to a trajectory. Okay, this is something quite important. In fact, we can link it quite strongly with the Koopman operator, because we can construct a very specific RKHS H, which encompasses all the HT, okay? And the UT is a restriction to HT on the Koopman operator on this specific RKHS. So we have a strong link between them. So we have demonstrated this in a paper which has been recently published. So now, in fact, with these assumptions, what happens is the following. In fact, we are building an isometry, an inequality between inner product between time t and time t0. So if I take the RKHS inner product between two feature maps at time t, okay, I use the definition of the Koopman operator of the RKHS. We have shown that it's unitary, so if we use the adjoint, we can write. Okay, we can use the adjoint and write this at time t equals to 0, and since it's unitary, that's identity, and we have this. Now we can use the reproducing property, and what we see is the following: is that the evaluation of the kernel between two ensemble members at time t is the same that the evaluation of the kernel at time t to 0. So we have remained constant the evaluation of the kernel along the trajectories. So the kernel is really attached to the trajectories, not to the state of the system. But here, what happens, and we were quite surprised when we have seen that, if I want to do kernel interpolations, the linear combination coefficients, they depend only on the kernel, and in fact they become constant over time. So if I have, I find a new ensemble member at a given time, at the initial time, okay, for the initial condition, then when we propagate, the linear combination remains the same. So this will give us a large versatility for data assimilation techniques. Of course, for a very long time, we will see just later the limitation of this. So we are able to define the infinitesimal generator of this Koopman operator. So it's just dependence time. We have shown that it behaves well, it's bounding, it's Q-symmetric, it's diagonalizable. This is just the exact, this is the theorem, just copy-paste from our paper. So what's important is the following. So in fact, we have a point spectrum in that case, but thanks to the RKHS. And here, AU, everything depends on time. And we have eigenfunctions that depend on time, eigenvalues. But here, the eigenvalues are constant along time. They are constant. And in fact, the eigenvectors, the eigenfunctions, sorry, the eigenfunctions, we have an exponential relationship between time to 0 and time t. So in fact, we have constructed a lax pair, if someone knows about it. We have to be a little bit careful because since we are changing space, like in the previous slide, sorry. Here we are changing space from H0 to HT. So we have to be a little bit careful in the, so for the infinitesimal generator, it goes to L2. So we need to introduce this injection into L2. So this is just a detail. So, but in practice, in fact, we can compute them. Okay, we can compute these eigenfunctions. So we can define a matrix M, which is basically this matrix M is basically the evaluation of this operator, infinitesimal generator, and we can compute this in practice, and we can evaluate it at time equal to 0. So in practice, for instance, if we have take a Gaussian kernel, we can differentiate it. And having an explicit expression which up to the knowledge of the time derivative of the initial states. So we can compute the evaluation of the Koopman eigenfunctions at the initial time. And here I go to the limits that I wanted to show. So here we have then this gives us access to the tangent linear operator, at least restricted to the RKHS family, and we can define modal Lyapunov exponents. So since we have the tangent linear operator, if we take an observable, we are able to propagate it. And if you take an observable which is aligned with a Koopman eigenfunction, we can relate, associate to each mode Lyapunov time, which is basically directly linked to the eigenvalue of the Koopman eigenvalues. And what we can do is that now if we want to do kernel reconstructions, we can expand the kernel onto the Koopman eigenfunctions, and basically, when we do the reconstruction, we can switch off modes which have passed the predictability time. So this is something that helps. I will not have the time to show results for that, but we have some results of the paper, and it helps predictions. Okay, here we go to some results. So here we start with the toy problem. It's a surface quasi-geostrophic model. So it's a transport equation of buoyancy. It represents more or less large-scale structures in oceanic flows and is able to produce small-scale turbulence. So what we have an ensemble of low-resolution simulation, and we have as well one high-resolution observation to get observation. In the high-resolution, in fact, we have some a generation of small scales. This is a low resolution. We have a generation of small scales here, in this state. And what we can do is in the RKHS family, we are able to rewrite an ensemble Kalman filter. So in ensemble Kalman filter, what we do is that we have the ensemble, and then when an observation arrives, we update the ensemble members such that the average is correspond to the minimum of this cost functional, and the variance is the inverse of the Hessian of J. So here, what's new is that since we do this in the RKHS, first we are able to collect, since we are searching for a constant in time linear coefficient, we are able to collect several observations before doing the update. So this gives a large flexibility for data assimilation. And more or less, in terms of penalty, here we penalize with the kernel. This is equivalent to penalize with the RKHS norm of the feature map. So we try this for an empirical covariance kernel, which is almost using identity, or Gaussian kernel. So here we rewrite the Kalman scheme in this situation, where we have a Kalman gain, the analyzed covariance matrix, and the linear coefficient of the ensemble. And this is what we have. So this is the error a long time. So if we don't filter, we have the error that is growing and the variance exploding. That are the stripes. Okay. If we use a standard ensemble square root filter, this is the gray line that we have. Now, if we just use the possibility to aggregate in time some observations, we see that it helps. Okay, it helps to reduce the error. Now, since we are playing with the RKHS, we can play with the penalty term. So here we just increase the penalty term, and this increases the variance without too much penalty into the mean error. And now we plug the Gaussian kernel, and this is what we have. So what is nice, first, we reduce the error, which is very nice. But as well, we increase at the same time the variance, which is very nice as well, because it gives some robustness to the filter. And so there are two main reasons why it works. First, we are performing better reconstruction by linear combination. And second, we are penalizing with off-diagonal terms, and these off-diagonal terms, basically, if we have two ensemble members which are very close, we are penalizing this. So we are improving the quality of the sampling as well. So this is just some visualization of the same thing. So this is a reference. This is a high resolution downsample and filtered and downsample. This is the classical techniques, where here we have reconstructed state, the error, and the variance of the error. And as you can see here, with the Gaussian kernel, we improve the quality of the reconstructions. We don't have these small things. And we reduce the error and we increase the variance. This is exactly consistent with the previous graph. So now we go to realistic or semi-realistic simulation. So now we are not anymore in the capability of a laptop, but we are running this on big GPU. So this is a quasi-geostrophic multi-layer simulation. It's written in primitive variable, but we use a projection onto the quasi-geostrophic dynamics. So 3 layers, yes, 8.5 kilometer resolution, and we have 65 ensemble members. So this is the domain that you have. So we take the North Atlantic domain. It's semi-realistic. It's a flat bottom, okay? But we have realistic coasts, and these are some observations along. This is a kind of, so we take a true swath of satellite altimetry, but of course we just use them as a mask, and we use synthetic observations that we know for that. So we are measuring altimetry, so it's a height of the seawater. If we collect observation during a period of 30 minutes, this is the kind of mask we have. And if we wait 1.5 days, this is the kind of coverage that we have. And something additional as well is that we can use another ability of the technique is the following. So in this time period, we are building a family of RKHS with fixed constant in time coefficients. We are taking observations, and then we are doing the updates. So before, we are doing the updates, and we were continuing here. So, but what we can do, everything has been defined at the initial time. So what we can do is that going back and run the ensemble from T0, having a kind of spin-up and continue. So this helps to, first, because everything has been defined at the initial time due to the Koopman operator technique. And this allows us to have a kind of spin-up to evacuate some eventual artifact due to the recombination of coefficients, and then to continue assimilation. So this is backstitch gives you the backstitch assimilation. So this is the kind of error that we do, that we have. So similar graph than before. If we don't filter, the error is growing a lot, and all other filters behave quite well. Here I just zoom. The standard technique, so ensemble square root filter is the blue line. If I use the Gaussian kernel and wait 1.5 days before doing the assimilation, it is this line which is consistent with the results we had before, but with the smallest gain in terms of performances. And if I use the backstitch technique, we improve better. This is the kind of state that we have. So this is a Gulf Stream. You can see here the Gulf Stream. I'm showing vorticity, potential vorticity. And okay, all techniques are able more or less to reconstruct quite well the technique. So in fact, the ensemble is quite narrow because we have only 65 ensemble members. But if you look at the error here, this is a standard square root filter with a Gaussian kernel, and here we see that the error is decreasing with the backstitch technique. And we have several layers, so it's if we go more in depth, this is the kind of results we have. Okay. Just to summary, we have defined a mathematical construction which is adapted to large-scale dynamical systems. We use RKHS to do a linear combination between observables. We have an isometry between time such that the linear combination coefficients are constant along time, and this leads to high versatility for data assimilation. We have some perspective to increase have more realistic configurations, use localization techniques, and maybe couple or extend with more advanced techniques. This is a very open statement. Thank you.